Well, thank you very much for the introduction. Thank you very much, especially Barbara, for giving me the opportunity to present my work. So I will be talking about the topic of optimal transport and production processes. I will be, so we have seen a lot of mathematical theories about Riemann geometry, infinite dimensional Riemann geometry. I will be extremely, I wouldn't, there's nothing abstract in my talk. I will be extremely concrete. I will be talking using in the setting of positive operators and Gaussian measures in the processing. So everything will be extremely concrete, so there's no abstract theory. I have a lot of slides, but I will not cover everything. So I tend to talk quite fast, so please slow me down. Go too fast. Sorry, I'm used to using my. Okay, so the purpose of this line of work I have been working on in the last recently is the generalization of the following geometrical structures for probability density function in Rn to the setting of probability measures on Hilbert space H. In particular, we care about Gaussian measures on Hilbert space and Gaussian processes. So Gaussian processes square integrable paths correspond to Gaussian measures on Hilbert space. And in a marginal setting of stochastic processes, we have the geometrical structures of the covariance, the corresponding covariance operators. So for general stochastic processes, we only have the second order structure with the covariance operators. I'm talking about the optimal transport and the Fisher-Rao metric and distance and the divergence. So that's a lot of there are a lot of results. I wouldn't see how much I can cover in the talk, but it does involve a lot of it does involve a lot of fields. So it involves operator theory, especially positive operators on a Hilbert space, kind of generalizing the theory about positive definitely matrices to the infinite dimensional setting. We do utilize Riemann geometry in the infinite dimensional setting, but just for Hilbert space, so it's a lot simpler than what Martin Bauer was talking about in the morning. And for Gaussian measures on Hilbert space and the correct production processes, and for the so these will give us a lot of results, but for more concrete results, we utilize the methodology of reproducing kernel Hilbert space, or RKHS, and the probability theory on binary Hilbert spaces when we do the sample complexity for estimating finite-dimensional results, estimating infinite dimensional formulas using finite-dimensional versions. So the kind of the last is kind of RKHS is really, my background is actually in RKHS. Actually, I got my thesis on my PhD thesis on RKHS, so I'm actually very interested in anything that involves RKHS. But in the finite-dimensional setting, we have a lot of results using Gaussian measures and symmetric positive or SPD matrices. We have, so of course, it plays a central role in probability theory and statistics and machine learning, but they also have there's a huge number of practical applications. We have applications in brain imaging, we have applications in computer vision, radio signal processing, brain computer interface, so BCI. So it's a huge literature on these applications. We have a lot of, and in particular in France, there are a lot of researchers working in these fields. That is the finite-dimensional setting. So the motivation for the infinite dimensional setting, so motivation is, I give an example, is the setting of Gaussian processes. So suppose we have a nice compact metric space. For example, let's just talk about the interval from 0 to 1, and we have a nice collection of random variables indexed by t. So the Gaussian process is just a collection of random variables, so that will find finite points in t. We have a vector which is distributed according to a Gaussian measure. And a characteristic of Gaussian process is fully determined by its mean and covariance functions. Covariance function are given by these formulas here, and the covariance function is a positive definite kernel. So we just note it by GP of mk. Okay. So this is an example of Gaussian. So I'm just talking about the case here with mean 0 for simplicity. So this is a Gaussian process with the a covariance function being this one is the Laplacian kernel with when the a is equal to 1, and on the right hand side we have the Gaussian kernel where the Gaussian process where the covariance function is the Gaussian kernel. So because the Gaussian kernel is a lot smoother, so the paths are a lot smoother. And we have the Am I missing some slides? Oh, yeah, this slide was supposed to be first. We have the correspondence between Gaussian processes and Gaussian measures. We care about Gaussian process with square integrable parts. So this happens if and only if the mean function is square integrable and the covariance function satisfies this property, is called the trace property. And that's a classical result in the theory of Gaussian processes, square integrable Gaussian processes, that we have the one-to-one correspondence between Gaussian process with mean function m and covariance kernel function k, and Gaussian measures with on the Hilbert space L2 d nu when you measure, for example. And here we have the mean function and the covariance operator ck, where ck is the integral operator with the kernel k st. So this integral operator appears. It's a very important object in machine learning in the theory of RKHS, and we actually will use it later on for the estimation of our formulas. Okay, there's a large literature on in statistics, especially in functional data analysis, studying the different distance and divergence between the Gaussian measures in correspond to Gaussian process. We have a lot of results using the Hilbert-Schmidt distance. So let's consider the case where we just have the mean equal to 0. So we just care about the distance between the covariance operators. There's a lot of results using the Hilbert-Schmidt distance, and recently they also work employing the Wasserstein distance on the K-on divergence. Also in the context of functional neural networks. We'll skip the next slides because. So I would like to be able to move from the finite to the infinite dimensional. I wouldn't present like concrete results from the finite to the infinite dimensional settings. I would like to first to clarify what I mean by the finite dimension, the infinite dimensional setting in this talk. So of course we have if we consider the set of probability measures on Rn, for example, then it's also an infinite dimensional method. But what I'm talking about here is probability measures defined on an infinite dimensional Banach space. In particular, talking about Gaussian measures on a Hilbert space. So the first setting is like the non-parametric setting. So the second setting is the parametric setting, because you're talking about Gaussian measures. But in this case, because the Hilbert space is infinite dimensional, so we also have an infinite dimensional parametric setting. So this is a setting I'm talking about. It's now we're talking about measures, Gaussian measures defined on a Hilbert space. So as we move from the distance or divergence between Gaussian densities on Rn to the setting of Gaussian measures on the Hilbert space, some distances are straightforward and generalized. So the Hilbert-Schmidt distance, the Wasserstein distance, they wouldn't have the same formula. But if we talk about the Wasserstein distance, like the Fisher-Rao distance or the Quebec-Laplace on the Rayleigh divergences, these are not always finite because they can be, they're actually generally infinite. So we will talk about this. We first talk about the Wasserstein distance and its entropic regularization, and we talk about the Fisher-Rao distance and Quebec a little bit later on. So first, we talk about the optimal transport distance for and its entropic regularization for our Gaussian measures and for Gaussian processes. Optimal transport is a huge field in mathematics and recently has also become very important in statistics and machine learning. So suppose we have a nice metric space. For example, let's talk about Rn first and a nice cost function. So we were just talking about the square cost function in this talk. And let's consider the set of probability measures on X. So we solve this optimal transport problem. We minimize the expectation of the cost function of all choice measures of nu0 and nu1. So this is the optimal transport between the two measures nu0 and nu1. And in the case when we have, when the cost function is defined by dp, where d is the metric, then if we take the p root, and this one we have a metric, and it's called the p Wasserstein distance. In the Gaussian setting, we have with the square cost function on Rn, we have a very nice closed form formula. So this formula was worked many years ago. So it's given by this. So we have the square, the distance between the mean, and then we have the distance between the covariance matrices. When the mean is equal to, when the mean is the same, we have the distance between the covariance matrix is also called the Wasserstein distance. Now this distance is very nice. One property of this distance which is very nice because it's always well defined. it doesn't matter whether C0 and C1 are singular or not. This is a very special property of the Wasserstein distance compared to the Fisher-Rao or the Gaussian divergence, because for all the other distance divergence, we need C0 and C1 to be non-singular. This is always well defined, even if C0 and C1 are equal to 0, it's still very well defined. So such a very, we will see this. It makes a very big difference in the infinite dimensional setting. So the infinite dimensional version is the same. We have the same formula, and it has the same formula as the finite dimensional. So as I said, this is not the case with the other distances and divergences, and it has been applied to the Gaussian process setting as well. And so as I said, it's singular it's valid for singular covariance operators. Now, if it's not Fisher differentiable, so we fix one of these to be a variable, for example, then we have the gradient, but the gradient is actually unbounded in the infinite dimensional setting, is an unbounded operator. Optimal transport in general, of course, the exact optimal transport formulation is analytically, or in general, is analytically difficult and also computationally challenging. It can have like very bad sample complexities. So it has been analyzed a long time ago. It can have very bad. It can be exponentially bad. And then, there was a recent approach to do something called entropic regularization. We instead of just minimizing the expected value of the cost function, we add the entropic term here, so kind of the divergence between the joint measure gamma and the product measure mu and nu. And so this, so what I'm going to talk about is, I'm not going to talk about the numerical properties of this. I'm going to talk about the analytical properties of this in the Gaussian setting. And I'm going to show that by doing this entropic regularization, we actually obtain very nice properties. And these properties are very clear in the infinite dimensional setting. It's a very sharp break compared to the finite dimensional setting. Of course, when we do this, when we add this the entropic term, we have something, and then this OT epsilon dp here, mu is not equal to 0, so this one is going to bias, and so there's something called the Singhorn divergence where we do the debiasing. So we have Jean-Félix somewhere here in the audience. And so we subtract this term here, so we obtain a divergence. So there's a lot of work in machine learning using this, analyzing the properties, the theoretical and numerical properties of the Singhorn divergence. I'm just going to talk about the Singhorn divergence in the Gaussian setting. So now, in the finite dimensional Gaussian setting, so we solve this optimization problem. We solve it for two Gaussian measures on Rn. So it was the formula was worked out like a couple of years ago. And so this term here is actually the mutual information. It's expressed via the differential entropy. We have like differential entropy of mu0 and mu1 minus mu0 I minus h of gamma. And we use something called the maximum, this is the classical property of Gaussian density, the maximum entropy property of Gaussian density. So we have, if a random variable x has mean 0 in covariance matrix C, then the entropy is maximum if and only if x is Gaussian. And so by this property, the minimizer gamma of this problem has to be Gaussian. And so, so it has to be Gaussian. The gamma here has to be a joint Gaussian densities of mu0 and mu1. And we can, it has this form here where the covariance matrix is given by this formula here. We see it's a cross covariance matrix, and we can express this term, this mutual information. That's a Gaussian formula for this, and we can just plug it in, and we solve for the optimization problem. And so it can be done, and we have the Gaussian formula. This is the entropic OT, and then this is the Singhorn divergence where we do the debiasing. And so everything can be obtained explicitly. Now we have a term n, like the dimension n here, but it's actually where n is the dimension, but it's actually dimension independent. That's why it can be generalized to the infinite dimensional setting. So that is the finite dimensional setting. So where we have everything has a Gaussian formula. So let's move to the infinite dimensional setting. Now we have. So now we have the C here, it's an infinite dimensional covariance, so it's a compact, like a trace class operator. So this entropy term here is no longer well defined because we have all the eigenvalue going to 0. And but we still have this, we still have like the form of the, we have this mutual information here is still well defined, can be infinite, but it's still well defined. However, this right hand side here is not well defined. The left hand side is well defined, but the right hand side is not well defined, infinite dimension. We have a property, we have a property of the classical property of Gaussian measures on a Hilbert space when the dimension is infinite. The two Gaussian measures are either, so the densities in Rn, they're always like, they always have the same support, which is all of Rn. Whereas for the two Gaussian measures on a Hilbert space, they are either equivalent or they are mutually singular. So they have disjoint support. This is a break, a sharp break from the finite dimensional setting, and we have very clear criterion for this. There was a worked out like a long time ago. So this is the criteria, this necessary and sufficient condition for the equivalence of two Gaussian measures on the Hilbert space. So the mean, the difference of the mean has to be less than one of them is q, for example. So the difference of the mean has to be belong to the range of q to the power half, and the covariance operators have to be related in this form, where these are S here as a self-adjoint Hilbert-Schmidt operator. So if we shift the mean just a little bit, then they will just become mutually singular. And this is the result, like for a joint Gaussian measure, we have if gamma is a joint Gaussian measure of mu0 and mu1, then gamma is equivalent to mu0, the product of mu0 and mu1. If and only we have the covariance operator satisfy this condition, so they are related to gamma 0, where gamma 0 is a covariance operator of the joint measure of the joint measure. So they have to be related by this formula, and where this operator V here is a unique Hilbert-Schmidt operator with operator norm less than 1. So it was worked out like in 1973, so it was more than 50 years ago. And we can go, and using the result of Baker, so Baker actually has a series of papers on the joint measures. And so this is the mutual information between gamma and the product measure mu0 and mu1. So it's infinite if gamma is singular with respect to mu0 times mu1, and otherwise it's given by this formula, where this that here is the Fredholm determinant. So given the choice class operator A with eigenvalues under K, we can express the Fredholm determinant I plus A used by this infinite product here. So this one, so if we just have A before, then this is not well defined. If we have I plus A, where I is the identity operator, then this infinite series converges. And so the correct generalization of the maximum, we're probably using the maximum entropy property. So the maximum, the entropy is not well defined, but the mutual information is well defined. So the correct generalization of the maximum entropy property of Gaussian density to Rn, to Gaussian measures on Hilbert space is a minimum mutual information. We have talked about because the mutual information is well defined. So if we have two joint Gaussian measures, then the mutual information between gamma and mu x and mu y is minimum if only if gamma is a joint Gaussian measure. And equal again. And then with this operator V here is the Hilbert-Schmidt operator. And so we can plug this. So by this minimum mutual information, we have the same result as before. So the minimizer has to be a joint Gaussian measure of mu0 and mu1, and it has to be equivalent to mu0 times mu1. Because if it is not equivalent, then this thing will just become infinite. So it's automatically excluded. So the minimizer has to be a joint Gaussian measure, and it has to be equivalent to mu0 times mu1. And so we can employ all the previous properties, and we can plug this expression for the mutual information of the joint Gaussian measure, and then we can solve this optimization problem. So this is an infinite dimensional optimization problem because it's maximized over the set of Hilbert-Schmidt operator with norm less than 1, but it can be solved, and we can obtain a closed form formula for it. There's also an alternative method, which is kind of this solving something called the Schrodinger system, that we can solve for it. So we obtain the same. We obtain the same results. There's one more method, which using something called the von Neumann trace inequality. So there are at least 3 ways to obtain this solution. And so this is the closed form formula for the synchrone divergence. So here we have this m epsilon 0, or like ij here, is a chase class operator, and that here is a Fredholm determinant. So when gamma goes to, when epsilon goes to 0, we obtain the square of Wasserstein distance. When epsilon goes to infinity, we just obtain the square, the difference between the means. Now, I would like to say that so that's a difference between the finite and infinite dimensional setting here. Now, for the Boris versus Stein-Nielsen, this is when the mean is equal to 0. We have this formula here. This formula is modified on the set of positive Chase class operators. So C1 here has to be Chase class. The synchron divergence is well defined over a larger set, which is the set of positive Hilbert-Schmidt operators. C0 and C1 only need to be Hilbert-Schmidt operators. They don't have to be Chase class. So it's defined over a larger set of operators. So what are the properties of these two distances, the versus Stein-Nielsen and the entropic regularization? So they are both well defined. They are always well defined and finite, and including for singular covariance operators. We see before that the Kullback-Leibler divergence is only well defined when the two Gaussian measures are equivalent, will finite, whereas the versus Stein and synchron divergence are always finite. However, it turns out that the synchron divergence has many nice theoretical properties. It's differentiable. We can show that it's actually differentiable, whereas the versus Stein-Nielsen is not differentiable. I will show the gradient is actually unbounded. And the Barry-Center problem, for example, is much better behaved. Always has a unique solution, and it's always valid. Another property is with regard to convergence. So we have suppose we have a series of Gaussian measures on a Hilbert space, and we have this property that they converge. This sequence of Gaussian measures converge in the versus Stein distance to a particular Gaussian measures. A here, when the corresponding covariance operator converges in the Chase class norm. So this result was worked out also many years ago. But it turns out that for the synchron divergence, we only need the convergence. So this one is an if and only if, it's an if and only if statement. But for the synchron divergence, we only need the corresponding covariance operators to converge to the Hilbert-Schmidt norm, which is weaker than the Chase class norm. And so we can apply loss of large number of Hilbert space value random variables to obtain sample complexity. Now this one is an if statement. I'm not quite sure whether it's an if and only if. It might be an if only if, but I don't know. And I will show very shortly that the Hilbert-Schmidt compared to the Chase class norm, the Hilbert-Schmidt norm has nicer properties when we analyze sample complexity. Okay, so I said before, like well, synchron divergence, we did the Hilbert-Schmidt norm, but we can apply here loss of large number of Hilbert space value random variables for the versus Stein-Nielsen with the Chase class norm. So Banach space norm is an L1 norm, and we can actually apply loss of large number of Banach space value random variables to obtain convergence, like almost convergence. But it's difficult to obtain the rate of convergence with this Banach space L1 with the L1 norm. So we will now, because of the formulas, we show that the formulas we have like for the Gaussian measures on Hilbert space had the same, they had the same formula as in the finite dimensional setting. But these are infinite dimensional formulas, so they are abstract formulas, and we would like to be able to compute them or estimate them in practice. So the Gaussian process setting gives a concrete setting in which we can estimate these distances and divergences. So let's suppose that we sample like m points from this interval t, like t from 0 to 1. And so we obtain, and we given the, suppose we have two Gaussian processes with kernel K1, K2, and so we have the corresponding, given this set S, we have the corresponding Gram matrix. And so we can show that under, under certain conditions, we can estimate the infinite dimensional formula in L2. So this is the distance between the Gaussian measures in L2 by the finite dimensional formula in Rm. So where this one of them is kind of like a form of normalization so that we have convergence. Now, this formula here, so this is an Rm. This is the distance between Gaussian measures in Rm, and this is the distance between Gaussian measures on L2. So Rm, when we look at it, of course, it's intuitively, this one is the finite dimensional version of this, but formally it's not, because Rm is not a subspace of L2. So what we do to obtain the sample complexity going from here to here is by the use of RKHS methodology. So we use RKHS properties, because whenever we have a Gaussian process, we have a covariance function which is for some definite kernel, and so that's a corresponding RKHS, and we have operators within this RKHS. I'm going very briefly this RKHS because complicated, but just say that we have operators between L2 and HKI, and we can express the covariance CKI by the product RK star RK mapping from L2 to L2. Whereas, because we want to estimate the distance between L2 to L2, whereas we can also obtain the, if we multiply RK with RK star, then we obtain the operator between HK and HKI. And then if we have like RKI and RKJ star, then we have the operator mapping from HKJ to HKI. So we can represent everything, all the quantities using these operators between the RKHS. Okay, I'm going to skip this because it's too complicated. And then we can represent. So we can represent. This is the synchron divergence, for example. This is synchron divergence. We can represent them using the RKHS operators, and the same for the empirical version. We can represent using the empirical version of the RKHS. And we obtain the following. So this is the sample complexity of estimating the synchron divergence of the Gaussian measures on L2, and this is the finite dimensional version. I think I need to have a square. Yeah, I have to have like a square here. The difference between the two synchron divergence. So this is the finite dimensional sample complexity, where this kappa I here are kind of the maximum value of the kernel. So for example, if the kernel is Gaussian or the Laplacian kernel, this kappa 1, kappa 2 just equal to 1. So this depends only on the sample size m. So it's dimension independent. As I said before, it uses a lot of RKHS. It is like we relies essentially on RKHS methodology. So this is because we have this because the synchron divergence. When we have the convergence of the sequence of Gaussian measures, the convergence happens when the covariance operator converges in the Hilbert norm. So we apply a law of large number for Hilbert space value random variables to obtain this sample complexity. Whereas for the Wasserstein distance, we have the trace class norm. So it's like the L1 norm. So we have the Banach space value random variable. So where the Banach space norm is MP when P is greater than 1. Now, when P is equal to 1 is actually a much more difficult case. And so here, for this result, I need to assume at the moment that the dimension of at least one of the RKHS is finite. So let's assume that the HK2 is finite dimensional, for example. So we can also obtain the sample complexity of the Wasserstein distance, but then it's no longer dimension independent. It depends on the dimension. Or if it is infinite, then it becomes vacuous. Of course, now for the synchron divergence we talked about before, that's a factor of epsilon here. Now, when epsilon goes to 0, when epsilon goes to 0, we obtain the exact Wasserstein distance. But when epsilon goes to 0, this right-hand side blows up. So the result is vacuous. So it doesn't apply. It doesn't apply in the case when it approaches the Wasserstein distance. So it's so that's a kind of trade-off here. So we need epsilon to go to 0, but when epsilon goes to 0, it doesn't apply anymore because it applies, but it's no longer meaningful. And for this one, we need the dimension to be finite, otherwise it's also infinite. So we have that's a major difference here between when we do the entropic regularization and when we do the exact Wasserstein distance. So this only happens in the infinite dimensional setting because in the finite dimensional setting, the norms are all equivalent. So the trace class of the conversion are all equivalent. In this case, they are not. Okay, I'm going to skip. So before I was assuming that we have the exact covariance matrices, but we can also assume that we can estimate the kx from the samples as well. We can also obtain, but the analysis is basically the same. So I'm just going to illustrate some of the results here. So we have here to have two Gaussian processes with this Laplacian kernel with the different a, so equal to 1 and a equal to
1.2. This is actually with the different sample, actually kind of n samples of each process. So here, so I'm doing on the interval from t from 0 to 1 to the power d, where d equal to 1, d equal to 5, and d is equal to 50. So this is when, so this is the Wasserstein, this is like the Synchron, and the Hilbert-Schmidt. Oh, sorry, this is the top and the lower. Yeah, the lower one is the Hilbert-Schmidt, this is Synchron. So we can see that the convergence of the Synchron and the Hilbert-Schmidt distance are very consistent. Whereas for the Wasserstein, when d is very large, it becomes a lot slower. I think a kind of a dimension independent convergence for the Wasserstein distance is probably unlikely. I'm not, at least that's what I'm thinking. I'm going to skip this because it's a lot harder for the Gaussian mixtures because we do not even have a closed form formula for the finite dimensional thing. We have work. There has been some work in the finite dimensional setting for Gaussian mixtures, but we do not have a closed form formula for the Gaussian mixture models yet. Oh, that was the optimal transport. That was with the Wasserstein distance between Gaussian measures and Gaussian processes and the entropic regularization, and we showed that when we do the entropic regularization, we have some very nice theoretical properties. Now, we don't have so much time, so we'll talk about the Fisher-Rao metric and distance. This is really based on the work of Gabriel Larotonda, and but unfortunately, he has already left. So I'm going to probably the first, we will talk about his work only. Let's see. So let's, okay, so when we talk, so I'm just going to talk about the Fisher-Rao metric for Gaussian, in the Gaussian setting. So in the finite dimensional thing, we have Gaussian densities here, the set of zero mean Gaussian densities, and we have, so this is like, it's given, so it's fully given by, we have the closed form formula for the density, of course, it's characterized by the covariance matrix, and we can define the Fisher, we define the Fisher information matrix, and this in the Gaussian setting is positive definite. We have a Riemannian metric, Fisher-Rao metric, and we have a closed form formula. So this formula was also worked out like a long time ago, and because we have the correspondence between the Gaussian densities and zero mean Gaussian densities and the set of SPD matrix of size n by n, so we also have it corresponds to something called the phi invariant Riemannian metric on this set SPD. So we have everything has a closed form formula. So these are very well known, and we have a unique geodesic joining any pair of matrix A and B has a closed form formula, and we have the closed form formula for the Riemannian distance. So there's a lot of theoretical, a lot of mathematical properties have been proved for this metric. Now I would like to generalize this to the setting of Gaussian measures on a Hilbert space. Now this is of course not possible in general because these operators in general, this A is in because this operator like the inverse is unbounded, and then we have the log is also generally unbounded. So I'm just going to talk about the generalization of that of this. Okay, so the challenge is, so this formula doesn't generalize directly right to the infinite dimensional thing because because this one is like unbounded, and then we have, and there's no natural reference measure because we don't have the Lebesgue measure on an infinite dimensional space, and so we cannot really talk about like a natural density functions, and so. In general, we cannot generalize the Fisher metric, the Riemannian metric the Fisher-Rao Riemannian metric doesn't generalize directly. So this is the work of Larotonda. So kind of let's try to generalize this for this distance directly to the infinite dimensional setting. So okay, this is what they did actually. Using the extended Hilbert-Schmidt operators norm and inner product. I can skip this because I think this is a more audience of mathematicians. I don't need to talk about this. Okay, so because we have A is strictly positive, right? So they have related eigenvalues all going to 0, and so that's why the A inverse is unbounded. And so what we need, and so this operator is generally unbounded unless it's only bounded under certain assumptions when we assume that the Gaussian measures are equivalent. So what we can do is we can do. Now in mathematics, of course, mathematicians talk about unitization. So we add like a gamma I, where I is the identity operator. So this A plus gamma I here now is strictly positive definite, and then this operator is bounded and the log is also bounded. Now, in machine learning, inverse problems in applied math, we talk about regularization. So I kind of go back and forth between regularization and unitization. But I really think in terms of regularization, because this is actually a universal theme in machine learning in inverse problems. And so this operator is bounded. When we do this unitization or regularization, this operator is bounded. But this is, if we take the Hilbert-Schmidt norm of this, then in general it's equal to infinity when gamma is not equal to mu. It's only finite when gamma is equal to mu. This is because the identity operator is not Hilbert-Schmidt. And so the resolution is to add, to extend the Hilbert-Schmidt, to extend this class of Hilbert-Schmidt operator. So it also includes the identity operator. So we have the extended Hilbert-Schmidt operator, and then the extended Hilbert-Schmidt norm and inner product. So we have this here. So now the norm, the extended norm of the Hilbert-Schmidt norm of the identity operator is equal to 1 instead of infinity. And then we consider the set of all extended or as Rotunra call it, unitized Hilbert-Schmidt operator of this form. And so it's an open subset in this Hilbert space. And so it's an infinite dimensional Hilbert manifold. And we have the, we can generalize the phi invariant Riemannian metric to this set, and then we have a very nice, we have like Katan Hadamard manifold, and we have so everything from the finite dimensional setting generalized to this setting. So we have, for example, the unique geodesic joint pair operators, and we have the Gaussian formula for the Riemannian distance. So everything here, of course, we do the unitization, and then we use the extended Hilbert-Schmidt norm. And so this can be. How much do I have? I have 10 minutes left. Okay. Okay, I will talk for 5 minutes. Okay, so what we can do is we can consider the set of all. So of course we can. So we don't have the formulation for the set of all Gaussian measures on the Hilbert space, but we can have the formula for the Riemannian metric for the set of all Gaussian measures, which are equivalent to a fixed Gaussian measures. And this is actually something that has been done in the some in the literature where we have researchers who study like the kind of infinite dimensional binary manifold probability measures equivalent to a given one, or Hilbert manifold probability measures equivalent to a given one. But this work are all very abstract, and I'm just talking about Gaussian measures which are equivalent to a fixed one, and in which case we can, okay, this is a condition for the equivalent. And so we can, let's fix the Gaussian measure mu0, and then and we consider the set of all Gaussian measures which are equivalent to this mu0, and so this the covariance operator has to be related to C0 by this formula here. Remember that we have the so that they are equivalent. So so this set is parameterized by this manifold, the manifold of all Hilbert-Schmidt operator, so that I minus s is greater than 0, and so we have an infinite dimensional Hilbert manifold, and we can compute the Fisher-Rao metric. So it's given by the this is the Radon-Nikodym density of mu with respect to mu0, and this is the Fisher derivative of this quantity here at s in the direction v, where this v1 and v2 are in the tangent space, which is just a self-adjoint Hilbert-Schmidt operator. So we can compute. So this is the formula for the kind of the definition of the Fisher-Rao metric, and we can solve for this. We can compute this explicitly. Okay. And we obtain this formula. This is the formula for the Fisher-Rao. So we have a Gaussian formula, and in the set of corresponding covariance operators, we have the same. Basically, we have the same expression x in the finite dimensional setting. So when we restrict to the set of Gaussian measures, we are equivalent to a fixed Gaussian measure. Then we have the direct generalization to the infinite dimensional setting. And we can compute like the Leibniz-Vita connection. We can compute the curvature tensor, the Riemann curvature tensor, and we can compute the curvature. We compute the geodesic and the Riemannian distance. So basically, it generalizes directly from we have the same formula. So we have the same formula as in the finite dimensional. So how is it connected to the distance between the positive definite operators? So it turns out that if we have this is on the left hand side, we have the formula of the Riemannian metric as in the work of La Rotonda. So when gamma goes to 0, it turns out that when gamma goes to 0, we do recover the exact distance of the two equivalent Gaussian measures. So to summarize, for the Fisher-Rao distance between two Gaussian densities on Rn, we have a closed form formula which is always finite. For two equivalent Gaussian measures on a Hilbert space, we also have the same formula, except we're using Hilbert-Schmidt norm, but they have to be equivalent. And when we do the regularization, then we obtain a distance between any pair of Gaussian measures. It's always finite. So what we do is we do the regularization, and then we do the extended Hilbert-Schmidt interproductive norm. And when the Gaussian measures are equivalent, and if we let gamma go to 0, then we obtain the exact distance. So why is it useful? Because we can, as in the case of the Weierstein distance and the synchron divergence, we can do the estimation as well. And we can estimate the Fisher-Rao distance between two Gaussian measures between two Gaussian processes using the finite-dimensional version. So we have the same analysis with the Hilbert-Schmidt norm convergence and with using the Hilbert space value random variables, and to obtain the sample complexity using the RKHS methodology. And so here, this is the one illustration. Here we have the two Gaussian processes with the Laplacian and the Gaussian kernel, and this is the estimation of the Fisher-Rao distance. And here where m is the sample size when we sample like m points on the interval t 0 to 1, and m going from 10 to 1,000, and gamma is 10 to the negative 6. And this is the case when we have two Gaussian processes corresponding to Laplacian kernels. So these Gaussian processes are much more similar than the previous two. And so the distance is a lot smaller. It's a lot smaller. It's going to go, so we have the conversion, but it's a lot smaller. This one is like less than 50, so it's a lot smaller. Okay. Okay, I'm going to skip the divergence. So thank you very much. Okay, I'm going to summarize first. I want to summarize. So we have the we can generalize from the finite-dimensional setting to the infinite-dimensional setting. We can have some formulas, but we have to restrict in the set of like equivalent Gaussian measures. And when we do not have equivalent Gaussian measures, then we can do regularization for the in the case of the Fisher-Rao metric or distance. And in the case of the optimal transport of the Weierstein distance, we do not have to do the regularization to obtain the formula, but the entropic regularization leads to many nice theoretical properties, especially when we have in the setting of in the Gaussian process setting where we want to do the finite-dimensional estimation, when we have like dimension independent sample complexities. So I will stop here. Thank you very much for listening.